All right, today I'm going to show you guys how to use a dot structure to then know the shapes of molecules, and again, the shape of the molecule determines how it behaves, so it's very, very important to do. And it's called VSEPR Theory is what we're using to do this. That's valence shell electron pair repulsion theory. And the bottom line is it says that the bonds and the lone pairs of electrons around the central atom will get as far from each other as possible in three-dimensional space, and that'll determine the shape of the molecule. And so if you know the number of bonds and unshared, or these would be lone pairs, they're not being shared in a bond, then you can determine the shape of that molecule. Again, doing these things at home, we would have people, in class memorize the shapes and the bond angles and all of that. But you're still going to have to know how to do dot structures to be able to get this. It's not going to make any sense if you can't do a dot structure. So anyways, I'll show you how to get all of these different shapes and molecules on the next page. And again, so like I said, the first thing you got to do is be able to do a dot structure. I've got a lot of information on here already for you because I didn't want you to have to be watching this video forever as I'm going through these. So if you want to get this information, you might pause it and write it all down ahead of time so that you're not, scrambling to try to keep up with what I'm doing. So the first thing you got to do to determine the shape, bond angle, all this information here across the top is actually do a dot structure. So remember, to do a dot structure, you've got to determine how many electrons all the elements need. Remember, they all need 8, except for hydrogen, which needs 2, beryllium needs 4, and boron needs 6. And then you have to subtract the number that they have available, and that's based on where they're at on the periodic table. So nitrogen is one of the normal atoms that needs 8, so it needs 8 apiece. There's 3 of them. So it's carbon and oxygen here that we're talking about. So the carbon and the 2 oxygens, they need 8 apiece. And when we look at how many they have available, oxygen's in column 6, so each of the oxygens needs 6, and carbon's in column 4, so it needs 4. So 24 minus 16 is 8. 8 divided by 2, that means there would be 4 bonds there. So we're going to put 2 bonds here, 2 bonds there. Then the next thing you do is, so that S equals N minus A will determine the number of bonds. You absolutely have to be able to do that. And then you go and add dots to all of them, make sure they all then have 8. That's all you got to do to make a dot structure. So right now that oxygen thinks that each of those bonds represents 2 electrons each. That's a total of 4. The carbon and the oxygen are sharing them, so they both think they have 4. So oxygen needs, that there's 5, 6, 7, 8. You're adding dots until each element has 8 electrons. Now the carbon in the middle, it's got 4 bonds. Each bond represents 2 electrons, so it has 8 to share. Doesn't need any dots around it. And then the oxygen at the end over here also needs 4 dots around it to have 8 total. So remember, you're determining number of bonds and then adding dots until they have 8, and that's how you do a dot structure. If you do enough of them, again, it should be a pretty simple thing to do. So the next thing we got to do to determine the shape of the molecule is, because we can look at it right here and go, well, it looks like it's linear to me. It looks like it's in a line. But this is only 2 dimensions, obviously. So when you start getting into these 3-dimensional structures, the way it's drawn is not actually how it looks. And again, I'll show them to you here in a second. And there's a website I can send you to, or a FET that I can send you to from Colorado State, where you can, again, see the shapes in 3 dimensions. So, all right, so the next thing we need to know to determine the shape is the number of bonding sites and the number of unshared pairs, or again, lone pairs of electrons. And that's on the central atom that we're talking about. So the central atom is carbon. So the number of bonding sites, a single or double or triple bond is 1 bonding site. So there's a bonding site and there's a bonding site. So it has 2 bonding sites on that central atom. Unshared pairs, again, or lone pairs, same thing. We're only, again, talking about what's on the central atom. So that's what we're looking at there. The carbon, because what's on the central atom will determine the geometry of that molecule. There are no lone pairs. There are no dots on carbon. So there's 2 bonds and no unshared pairs. You can go back here and see that 2 bonds and no unshared pairs makes a linear molecule. Again, I built it for you. This is what it actually looks like. and each of those flexible arms there represents a double bond on that carbon, and you can see that it is a linear molecule. You know, when you compare, obviously just looking at the shape, it's a linear molecule. Bond angles, again, between the outside atoms there, between everything that's on the central atom, the bond angle between the two oxygens is half of 360. The whole thing would be 360. So again, half of that would be 180. So the bond angle there is 180 degrees. Polar and nonpolar. Now, here's the thing. For a molecule, we'll talk more in the future about polarity of molecules and so forth, but the bottom line is this. If you have a molecule that has, let's just say it's got two different atoms on the outside like that, they don't share electrons equally. One has a greater electronegativity, we talked about it much earlier in the year, than the other, and so whichever one has the greatest electronegativity here, this is oxygen and that's carbon, the oxygen would be more attracted to electrons than carbon, so it'd be slightly negative, and this side's slightly positive. So when you have a molecule that has a positive and a negative side, we say it's polar. Now there's some ways to know whether or not a molecule is polar. First of all, if a molecule is symmetrical and all sides are the same on the outsides, we say it's nonpolar. So no matter how you look at this, each of the oxygens are negatively charged, but if we brought another one next to it, they would repel each other. So when you have the same charges on the outside, slightly negative, then that's a nonpolar molecule. So this molecule is nonpolar. Now I want to point out what it takes to be polar. So if the molecule is symmetrical and all sides are the same, that is always when it's nonpolar. But if the molecule might be symmetrical, but if all sides are not the same, in other words, if we replace this oxygen suddenly with a nitrogen, then the sides are not the same. And the oxygen and nitrogen, they don't have the same electronegativity, so they don't have the same attraction for electrons. So that means compared to each other, one would be slightly negative, the other slightly positive, and then suddenly it would be polar. So polar molecules are molecules that are lopsided. They're also molecules that have any unshared pairs on the central atom. That would make a polar molecule. So this is nonpolar. Both sides are the same there. All right, the next one. Again, we got N minus A. We got all of them need 8 apiece. Available, the oxygens need 6. Carbon needs 4, but it's -2, and that affects A. You got to add 2 extra electrons to the available electrons. So 32 minus 24 is 8. 8 divided by 2 is 4 bonds. 1, 2, 3. And to add the 4th bond in there, you're just going to have to pick a side, and we're going to put that extra bond right there. And so there's our 4th bond there. Then remember, you got to go back and add dots until they all have 8. And so we're going to put 2 there. We got to add 6 dots to this one so that it has 8, because remember that bond represents 2 electrons that they're both sharing. This one over here also has 8. You got to look at the central atom though, because that determines the shape. And it thinks it's got 2, 4, 6, 8. Doesn't need any dots around it. So right now the number of bonding sites, remember a double bond counts as 1 bonding site, so it has 1, 2, 3 places where there are bonds. Unshared or lone pairs, again, that's what's on the central atom carbon. Doesn't have any. 0. So the shape of that molecule, what's going to happen is, again, that looks like a T right now, but those oxygens, they all are sharing electrons. They're going to get as far apart as they can possibly be, so it's actually going to look like that. There's our double bond there. But again, they don't take up any more space than the single bonds, and so the oxygens, again, they're all attracted to the electrons, and they get as far apart as possible, and that's what that molecule is going to look like. And so the shape of that molecule, and again, I want to show you, it's here too. 3 bonds, no unshared pairs. It looks like a triangle on a plane, so that the name of that shape is trigonal planar, because it's like a triangle on a plane, obviously. And the bond angle, and again, it's not still just a 2-dimensional structure. It would be 1/3 of 360. So the bond angle between each one of those is 120 degrees. Now, again, notice there's symmetry on all sides. All sides, I know you got a double bond here, but that doesn't matter. You got oxygens on all sides. They're as far apart as possible. They all have a slight negative charge. If you brought another molecule like this, it would repel each other. And so when you have the same charge on the outside and you have symmetry, that's a nonpolar molecule. the significance of things that are nonpolar. When the molecule is nonpolar, they typically don't stick together very well, and a lot of those are gases. So gas molecules are nonpolar. And then when you start having polarity in molecules, then you get to your liquids and solids. All right. So let's look at the next one. We've got, again, needed electrons, 8 apiece, that's 24, and then 6 and 6, and nitrogen needs 5. It's in column 5, but it's got 1 extra electron. Now you got +1 here, but it's -1. That remember, it has an extra electron. That's why I'm saying it's got 1 more electron than it should have. So that would be 24 minus 18 is 6. 6 divided by 2. Going to have a double bond over there and a single bond over there. We've got 3 bonds on it. Then go back and add dots until now oxygen thinks it has 8. Nitrogen right now has 2, 4, 6. It needs 2 dots there. So to have 8 total electrons. So you don't forget what you're trying to do when you're adding dots. You're trying to make sure they all have 8. That's why they bond together in the first place, just so that they can all have 8 electrons total. Now, number of bonding sites on that central atom. It's got 2 bonding sites. But now, see, it has an unshared or a lone pair of electrons right there. And they take up space as well. So on paper, you know, right now we're looking at it and go, well, it looks to me like it's linear. But again, the structure doesn't really look like that. Because the unshared pair of electrons take up space, so the structure looks like this. That paddle represents the unpaired electrons that are taking up space. Because this bond is electrons, and this is a double bond of electrons there, and so that molecule looks like that. So when you consider the shape of the molecule, what you look at actually is the orientation of the atoms in that molecule. So I'm going to cover up our unshared pair there, and that's what that molecule looks like. And so the shape of that molecule, it is bent, and that's what it's called. So it is called a bent molecule. Now, the bond angle here between these two, the bond angle between everything is still 1/3 of 360. So in this case, it's 120 degrees. And again, it's a symmetrical molecule, but are all sides the same? They're not. This is a pair of electrons. This is oxygen. So in this case, whenever, you know, for a molecule to be nonpolar, it has to be symmetry on each side, and all sides have to have the same atom on there. It doesn't have that. So this would be what we would call a polar molecule. Polar just means that one side of the molecule would be, you know, positive, the other side negative. In this case, more negative than the oxygens there, so it makes a polar molecule. All right, next one, CH4. Again, carbon needs 8, but hydrogen is an exception, only needs 2, and there's 4 of them in there, so that's 16 total. Carbon, again, is in column 1, so it has 4 available. Hydrogen's, I said carbon's in column 4, has 4 available. Hydrogen's in column 1, each one has 1 available, so 16 minus 8 is 8 divided by 2 to get bonds. 4 bonds there, need a little space there for that bond. So again, the central atom there, the carbon has 4 bonding sites, number of lone shares or unshared pairs. Again, we don't need to add dots to any hydrogen, because remember, you're adding dots until they have 8, but some elements like beryllium and boron, beryllium only needs 4, boron only needs 6, but hydrogen only needs 2 electrons, and each bond is accounting for the 2 electrons that it needs. It's sharing them with carbon, and so there are no dots needed for hydrogen, because hydrogen doesn't need 8 total electrons. So there are no unshared pairs around carbon. Again, we look at it like this, and again, that's a 3-dimensional structure. For the hydrogens to get as far apart as possible, that molecule is going to look like that. And so now we got 3-dimensional structures, which is why, again, everything on paper doesn't make any sense when you start trying to call these shapes, these molecules. This shape is a tetrahedron. So it's a tetrahedral shape there. You know what? This, I'm going to have to redo that one real quick, because that carbon is not the carbon that I actually needed there. Because that did not look like a tetrahedron, and I'm not going to start this over. So real quickly, let me do that for you. And here you go. So that is a tetrahedral shape. So the problem was that carbon was an exception. It had 5 places for bonds there, but this is regular carbon, which only has 4 places, and you can see the shape of that molecule there. And it's a 4-sided structure. Tetra means 4, so this shape of this molecule is called tetrahedral. So it is tetrahedral molecule. And the bond angle here, again, you can't say 1/4 of 360 because it's 3-dimensional structure. and you're just going to have to take my word for it. If we take the bond angle for any of those, bond angle there is 109.5 degrees. And again, this is represents methane here. It's a gas at room temperature because again, it's nonpolar. It's all sides are the same. All the outsides are the same. It's symmetrical. They all have the same element. Again, keep in mind if I took a hydrogen off and put a nitrogen on there, suddenly that makes it polar because they don't all have the same attraction for electrons. Because when you consider like the attraction for carbon or hydrogen, which one has the highest attraction for electrons, one of them would be slightly negative, the other would be slightly positive. But if this is slightly negative, all of them are. And so if you bring them together, remember, opposites attract in the atomic world and like charges repel. And so nonpolar molecules repel each other, so they're typically gases at room temperature. So that's why methane, being nonpolar and small, is a gas at room temperature. All right, next one. Again, needed electrons, 8 for, again, this is phosphorus here, or nitrogen, either way. And hydrogens need 2 apiece, so that's 14. Available electrons, phosphorus is in column 5, and hydrogen's in column 1. So 14 minus 8 is 6. 6 divided by 2, 3 bonds. I got ahead of myself there. There's 1 bond, there's 2, and there's 3. But don't forget, if that's the way you left it and you didn't complete the dot structure, you would get the shape wrong. Because right now you would think it has just 3 bonds and no unshared pairs, but you have to add electrons to make sure that phosphorus has 8 total. And there's its, it's got 2 here and 2 there. That's 6, 7, 8. Remember, for elements that are not exceptions, you need to add dots until they have 8. All right, so do that. And now we have number of bonding sites on that central atom is 3. Unshared pairs of electrons, 1. There's the unshared pair on the central atom there. And so that molecule looks like this. And remember, the paddle represents an unshared pair of electrons. And so, but when you consider the shape of the molecule, it is the arrangement of the atoms and how they compare to each other. So you cover this up and go, what does that look like there? And that actually looks like a tiny pyramid, which is why that shape is called pyramidal. And so this is a pyramidal shape. And keep in mind, guys, that this is where like I've said it all year, when there are benefits to doing these things at home and doing online tests, is that when you were in class, any other year, you're responsible for knowing all of these. But now you've got a reference for you to go. But the bottom line is, if you don't know it's 3 and 1, you're not going to get that it's pyramidal, and you're going to miss all this other stuff. So you got to be able to do a dot structure. So, anyways, so here's the thing. The bond angle for this is still the same. It's a 4-sided structure. So the bond angle for almost all of them are 109.5, but there is an exception. In NH3, the N is such a small molecule. If this is just nitrogen, so if this ammonia is what NH3 is, the electrons, N is such a small molecule, the electrons there take up more space, and it squeezes the hydrogens together. And so the exception to this is NH3 actually has a bond angle of 107 degrees between the hydrogens, because again, N is smaller than other atoms, and these unshared electrons take up more space, and they squeeze the actual bonds a little closer together. So NH3 is an exception to that. So NH3 would be a 3 bonds, 1 unshared pair, but the bond angle is actually 107. And remember what I said, polar, nonpolar. Are all sides the same? No. Those are electrons and those are hydrogens. That means this molecule is slightly polar. When you check the difference between here and here, they don't have the same attraction. These are actual electrons. Hydrogen's got a little bit of attraction for electrons, but they're not the same on each side. So we would say that molecule is polar. So not symmetrical. You don't have the same thing on all sides. Makes a polar molecule. All right, moving on. Next one, H2S. S needs 8. H needs 2 apiece, and so that's a total of 12. Number available. Sulfur has 6. It's in column 6. Hydrogen's in column 1. So that 12 minus 8 is 4. 4 divided by 2, be 2 bonds there. So it's going to look like that. And then remember, we got to add dots. We don't need to add dots to hydrogen because hydrogen only needs 2. Sulfur needs 4 more dots because it's got 2 there and 2 there for a total of 4, 5, 6, 7, 8. That's what you're adding dots in for. They have 8. So the number of bonding sites on that central atom, again, it's got 2 bonding sites, 1 there and 1 there. Number of lone pairs it has two. Again, there's one there and there's one there, and they stay together and they take up space as well. And so that molecule, you know, I didn't draw, let's see, I didn't put, the way these are set up, the oxygens don't have places for the actual two unshared pairs of electrons, which would be here. The unshared pairs take up more space than the shared pairs, so it makes the geometry of that molecule look like this. Like I say, the unshared pairs take up more space than the shared pairs. It forces the bonds, the bonded or the hydrogens closer together. So that molecule looks like that. We've already done one that actually looks like that. That's called a bent molecule. And water does this. Water is a bent molecule, and that's the fact that it's bent and not linear is why it's a liquid at room temperature. Because it's a really small molecule. Bond angle here, though, is again, if it would be a four-sided structure to do this. So the bond angle would be 109.5 for anything that's not water, but water is an exception. So H2O's bond angle, because again, oxygen is such a small molecule, the electrons on the outside take up so much more space, they force these hydrogens a little bit closer together. So the bond angle for water specifically is 105. And again, we've always, every chemistry book you're going to look at is going to tell you the exceptions to these, and you have to know ammonia and water are just to have a little bit different bond angle because the molecules, the central atom is so small. Again, when you look at this does not have symmetry on all sides. For it to have symmetry, we'd have to have hydrogens over here as well. This is a lopsided molecule. So when you're looking at this molecule, it's got electrons over here, hydrogens over here. It is polar. And like I said, that's what makes it a liquid at room temperature. All right, the next one. Again, these sometimes can get, sometimes you can have more than one central atom. And whenever you have a molecule that's larger, you want to put whichever molecule you have the fewest of in the middle, and hydrogens always have to be on the outside because, and you can never link hydrogen in more than one place because they can only make one bond because they only need two electrons. So here's the hydrogens, carbons, carbon needs 8 apiece, hydrogen needs 2 apiece, and so that's 24. And then number available, carbons in column 4, hydrogens in 1. So that would be 24 minus 12, 12 divided by 2, 6 bonds. 1, 2, 3, 4, 5. The 6th one goes there. But when you have more than 2 atoms, when you have more than one central atom, you actually have to pick a side. So we're going to pick this carbon as the central atom and look at everything attached to it. We could also pick the other one. The shape of each side is going to be exactly the same. And say how many bonding sites are on, each carbon atom. So 1, 2, 3 bonding sites, no dots on carbon because it already thinks it has 2, 4, 6, 8 electrons. So it's got 4 bonding sites, no unshared pairs. You can go up there and see that bond angle there with 4 bonding sites and no unshared pairs would be tetrahedral. Tetrahedral molecule. And again, if I would just attach another carbon to this, there's the extra carbon to be here and the hydrogen's not here, you can see the shape would be exactly the same there. So bond angle in a tetrahedral molecule, again, go up there, it's 109.5. Again, it's a 3-dimensional structure. All sides, again, would be the same on that one. And let's see, you know what? I'm not going to go out 20 minutes into this video, and that's 3 bonding sites. I messed this one up, so we're going to go back and fix it. 3 bonding sites, no, so 1, 2, 3, not 4. There's 1, 2, 3 bonding sites, no unshared pairs. 3 bonding sites and no unshared pairs. It's not tetrahedral. It is trigonal planar. And the bond angle is 120 degrees, and I actually have that one built here. So I made a mistake there. I started off, and so you can see there's our double bond there for the carbon in the middle. And so we got 1, 2, 3 bonding sites there, no unshared pairs, or 3 bonding sites, no unshared pairs. 3 and 0 makes trigonal planar, 120 degrees. When you're looking at this molecule, it is symmetrical, all sides the same on the outside, so it is nonpolar. So I apologize for that. That was not 4 bonding sites there. And now we'll wrap this up because again, this always takes a long time to do. So the last thing is molecules that actually, notice I don't have N-A there because these are actually expanded valence. We always say, they all need 8 in their outer shell, but sometimes that's not true. Phosphorus, PCl5 or phosphorus pentachloride can actually have 10 total electrons. You just need to understand that what the shape of this molecule would actually be. I would never give you one of these and tell you to do S equals N minus A to put it all together, but you need to understand that PCl5, this molecule here, it has 5 bonding sites on the central atom, no unshared pairs. The shape of that molecule, okay, each side looks like a pyramid. And in the middle, it looks like trigonal planar. So that's why it is a complicated name. It is called trigonal bipyramidal. So there you go. So that's trigonal bipyramidal. And the bond angles, again, you can look at them. Look at the top. That's a 90-degree angle there for the top and the bottom. But the middle part, if you look at all of those, so the middle part, that's a bond angle of 120 degrees. So the bond angle is 120/90 degrees. And again, no matter how you look at this molecule there, all sides are the same. It is symmetrical. It is nonpolar. And the last thing there, you can have SF6. It's expanded valence. It's got 12 electrons in the outer shell. 6 bonding sites, no unshared pairs on the central atom. And if this were a crystal shape, because a lot of these things do make crystals, this would be a 4-sided structure at the top. 1 face there, 2, 3, 4 there, and the bottom 1, 2, 3, 4. It's an 8-sided structure, and so that's called octahedral. And the bond angles, you can see them all. They're all exactly the same. They're all 90 degrees. And again, it is nonpolar. All right, the important thing is for you to be able to, again, use this resource to be able to determine shapes, bond angles, polar and nonpolar. But again, if you cannot actually do a dot structure, that's going to be a problem with this. And so good luck with that. And you'll have GoForma to be working on this stuff with. So good luck.